Hey guys, so we're going to start with chapter 3, which is all about energy. So in chapter 1 and 2 we talk a lot about matter, which we said was anything that has mass and occupies space. And now we're going to talk about energy, which is everything else in the universe that's not matter. Okay, so first I want to look at these couple of videos here, and they're basically two chemical reactions showing the opposite of each other. So on the left here you see we have water as a reactant. So water is what we're starting with, and it's going to produce hydrogen and oxygen from that process. And then on the other hand, if you take hydrogen and oxygen and combine them together, it will make water. So these are like opposites of each other, and we want to compare how they look the same and how they look different. Okay, so here's our first video. So we're going to make hydrogen and oxygen from water.
If we connect an electrolyzer filled with distilled water to a source of direct current, we can observe a slow evolution of gases. After some time, we notice that the volume of the gas released at the cathode is double that of the gas formed at the anode. To identify the gaseous products of the reaction, we collect each gas in a test tube and check its behavior in the presence of a glowing splint. The characteristic cracking sound proves that the gas released at the cathode is hydrogen. The ignition of the glowing splint is evidence that the gas collected from the anode is oxygen, which supports combustion.
Okay, so what we just saw there was, in the beginning, is if you run electric current through plain old water, then you'll see that you can get hydrogen and oxygen. And we can tell that it's hydrogen and oxygen in two different ways. One way is simply that you get twice as much volume on one side than you do on the other. So that's this side with twice as much is hydrogen. That's what this 2 means. We get twice as many hydrogens for every oxygen. And so what they did at the end was to test each one to use its chemical properties, like the fact that when you light hydrogen on fire it makes a loud cracking sound, to identify these substances. Okay, so that's proving that a chemical change occurred. Next we have the opposite reaction. If we take hydrogen gas and oxygen gas and mix them together, we can make water. And so in this one we were adding electricity into the reaction, right? We had it plugged into the wall, so we're adding energy. Electricity is just a particular kind of energy. On the other hand, if we go the other way, if you take hydrogen gas and oxygen gas, we should be able to produce energy. Okay, so let's see. Okay, so in this video he's got hydrogen and oxygen inside of a balloon, and the room is dark so that we can see how the reaction progresses a little better. And they're going to show us in slow motion. So here's a candle. He's got hydrogen and oxygen mixed together in here, and here's a little candle. You can't see him. He's actually right here. This is the instructor. And he's got a really long stick holding that candle, so he doesn't have to be close to the balloon for obvious reasons. Okay, so here's the slow-mo version. That's a really, really, really loud explosion that happens. Okay, so we have produced energy in a couple of different forms. The first thing that most people notice is the fire. So that's heat, and it's also light. And then also, as I pointed out, it's a really loud explosion. That's a kind of energy as well. Sound is energy traveling through space. So it's a kind of energy as well. So we're producing a lot of energy from this reaction. In fact, we're producing as much energy in the right-hand reaction as we put into the left-hand reaction because these are opposites. So one of them costs energy, and one of them produces the same amount of energy from that was used up in the prior reaction. So we can diagram this by drawing energy on the y-axis and the reaction progress on the x-axis. This is called a reaction coordinate diagram. It's a fancy way of saying we're just measuring or tracing how the energy is moving around. So, water has relatively low energy, and if we put a bunch of electricity into it, you can get hydrogen and oxygen, which are relatively high in energy. But if I take hydrogen and oxygen and I put them together to make water, that same amount of energy comes right back out. So here we're adding energy, and here we're taking energy away. In other words, we're producing it. Okay. This is called potential energy because it looks like a hill, right? And so we think about potential energy as if I hold something up off of the earth, I know if I let go it's going to fall. And when it falls, it produces kinetic energy. Before I let it go, that has the potential to produce energy, so it's called potential energy. So this reaction where we put energy in, this was in the form of electricity plugged into the wall. We put energy in, that is called an endothermic reaction, and we can actually write energy as a part of the reaction. It would be a reactant here. It needs to go in to make it happen. In this case, this energy that gets produced is the fire, the light, the heat, the sound, all of that. That is an exothermic reaction. So endothermic means reaction energy goes in. Endo means inside, the same way that endoskeleton means internal skeleton, so that's what people have. Exo means out or exit, so the energy is exiting the reaction. Exo, like exoskeleton, so like lobsters and bugs have that. Okay, so endo means within, exo means outside. Okay. Now, this leads us to the next topic. In order to measure heat, in order to talk about heat, we have to have units. We have to agree on what, how we're going to measure heat. So, one definition is a calorie. And this is used by scientists all over the world. It isn't the same as the calories on your food wrappers. We're going to cover that in just a second. It's worth noting that it's not the same as the nutritional labels. We call those nutritional calories. They're different. Related, but different. So, a scientific calorie is defined as the amount of heat required to raise the temperature of 1 gram of water by 1 degree Celsius. So 1 gram is 1 centimeter cubed. Okay, so here's our 1 gram of water. It's roughly a centimeter. That's a milliliter, by the way. So if you have a syringe handy, you can see that that's a pretty small volume. It's not very much material. It takes 1 calorie to heat that material up by 1 degree Celsius. So everything's ones. It's pretty easy to define it that way. So this is our 1 gram. If I have 260 kilocalories, 260 kilocalories, right? You'll notice the C is capital. That's because it's a scientific calorie. Nutritional calories are lowercase, just so you know. Anyway, so 260 kilocalories. I can convert that into regular calories if I remember that there's 1,000 of the base unit, in this case calories, for every kilo. Okay, so that kilo prefix gets used here as well. And so that means 260,000 scientific calories are being used here. So if I only had 1 gram of water, I could raise the temperature from 0 Celsius to 260,000 degrees Celsius. That's really, really hot. Okay, so that's a lot of energy. This, by the way, 260 kcals is about the amount of energy in a Snickers bar. Just to give you a reference. Okay, so if you were made out of 1 gram of water, just 1 gram, very small, and you ate a Snickers bar, it would raise your body temperature to 260,000 degrees Celsius. That's high. All right. So then the next question is, what other kind of units are we going to have? We have calories, kilocalories. There's also something called a joule. And as it turns out, 1 scientific calorie equals 4.184 joules. So in dimensional analysis, when we have an equality like this, you can turn it into a ratio. In fact, you can turn it into a ratio where you get calories or where you get joules. So it can go back and forth either way. This one would solve for joules, this one would solve for calories. Super handy. Okay, so nutritional calories are kilocalories. They're not actually just calories. And the reason for that is, like, if you bought a Snickers bar that said 260,000 calories on it, you probably wouldn't eat it. So marketing people, in America anyway, have changed to say, okay, well, we're going to lowercase the calories, so the little c means kilocalories. So if it comes off a nutritional label, you need to remember you've got to convert it to regular scientific calories before you can do any calculations. Okay, so there we go. Remember that. The labels are lies. I bet you're shocked. Okay, so you're going to pick up in video 2 with a discussion about how to use calories and kilocalories and what they all mean. But in the meantime, there's this one more vocab word that I want to define. Everything absorbs heat in different ways, right? So some things, when you put them in a hot boiling pot of soup, will be hot. So for example, if I make soup and I put a metal spoon in there and I put a bamboo spoon in there, one of them will be hot when I come back to stir the soup and the other one won't. And of course, the metal spoon is going to be the one that's hot. So that's not the one I'm going to grab. That's because metals have a really low heat capacity. And the symbol that we're going to use for heat capacity is an S. Different places, if you go online, some places define this as a C for capacity. Some people will even say SH for specific heat. Some people say S. So these all mean the same thing. There's no standard symbol here, but metals don't absorb heat very well. In fact, they absorb a little bit and then they want to pass it on as fast as they can because they're conductive. So they have a low heat capacity. Something like water has a relatively high heat capacity. So when we say low, by the way, we mean less than 1 for metals. And the units here are funny. Joules per gram degrees C. So the heat capacity of water is really high for liquid water. It's 4.184 joules for every gram and degree Celsius. That means if I want to heat water up, if I have 1 gram, I can raise the temperature by 1 degree by 4.184 joules. So this goes back to our definition for what a calorie is. All right, but this is something we intuitively understand. Like, you know, if you have a pot of soup with a metal spoon and a wooden spoon, you're going to use the wooden spoon to mix it with. You're not going to grab the metal. So we kind of intuitively understand heat capacity. Now we're going to use it to figure out just how hot things can get.